Let me take you back to a time when scientists were struggling to find order in the chaos of elements. Imagine having a puzzle with missing pieces and no picture to guide you. That's how the periodic table felt before Mendeleev. He introduced a bold idea that the properties of elements are a periodic function of their atomic weights. But there were gaps and inconsistencies. For instance, iodine had a lower atomic weight than tellurium, yet its properties matched more with fluorine and chlorine. Mendeleev prioritized properties over strict order, leaving intentional gaps for elements like gallium and germanium, which, fascinatingly, were discovered later with almost the exact characteristics he predicted. But something didn't sit right. It became clear over time that atomic weight wasn't the fundamental key. As chemistry advanced, especially with the discovery of electrons and protons, a new and more precise parameter emerged, the atomic number. This number defined an element's identity and aligned perfectly with chemical behavior. That's when the need to revise the periodic law truly crystallized. Have you ever seen patterns in unexpected places, like rainbows in soap bubbles or rhythms in waves? In 1913, Henry Moseley observed one such pattern hidden inside atoms. He studied X-ray spectra of elements and noticed something remarkable when he plotted the frequency of X-rays emitted by elements against their atomic numbers. The result was a perfect straight line. But when he used atomic mass instead, the line didn't hold. This breakthrough revealed that the atomic number, not the atomic mass, determines an element's identity and properties. And that led to the formulation of the modern periodic law, which states the physical and chemical properties of the elements are periodic functions of their atomic numbers. This law resolved the contradictions in Mendeleev's table and brought atomic structure and chemical properties into perfect harmony. It wasn't just a new rule, it was the beginning of a new way to look at the building blocks of matter. Now imagine walking into a well-organized library where every book is shelved by subject, theme, and depth. That's what the modern periodic table is for a chemist. The periodic table we use today is arranged into 7 horizontal rows called periods and 18 vertical columns called groups. Each period corresponds to a principal quantum number from 1 to 7, representing the main energy level that electrons occupy. And groups? Well, they bring together elements that behave like a family. They share similar outer electronic configurations, like cousins with matching traits. For example, all group 1 elements have 1 electron in their outermost shell, making them explosively reactive with water. This systematic grouping into S block, P block, D block, and F block gives the table its distinctive structure. It's not just about layout, it reflects deep atomic patterns. The periodic table is a visual map of electronic structure, and with IUPAC's universal numbering of groups from 1 to 18, it has become the common language of chemistry across the globe. Have you noticed how some rows in the periodic table stretch long while others are short? That's because the number of elements in each period is governed by how many electrons can fit in a shell. The first period, which starts with hydrogen and helium, has just 2 elements because only the 1s orbital is available. But the second and third periods, with 2s and 2p or 3s and 3p orbitals, accommodate 8 elements each. By the time we reach the fourth and fifth periods, d orbitals join the party, expanding the count to 18. And the sixth and seventh periods? They hold up to 32 elements each, thanks to the inclusion of f orbitals, though many of those are shown separately to keep the table compact. Groups, on the other hand, align elements with similar chemical properties vertically. For instance, Group 18 houses the noble gases, elements with full valence shells and very low reactivity. Understanding how periods and groups are structured not only helps us locate elements, but also predict their behavior, like knowing your classmates' personalities just by their seating arrangement. So, why does the atomic number matter so much? Let's think of it this way. The atomic number tells us how many protons are in the nucleus and, in a neutral atom, how many electrons are present. These electrons arrange themselves in energy levels or shells, and this arrangement, the electronic configuration, decides everything from reactivity to bonding nature. As we move across a period, atomic number increases by 1 with each step, and so does the number of electrons. This causes systematic variation in properties, like a predictable rhythm in a song. Whether it's the reactivity of alkali metals or the inertness of noble gases, it all traces back to atomic number. And unlike atomic mass, which can fluctuate due to isotopes, atomic number is absolute. It defines the identity of an element. That's why periodicity, the recurring trends in element properties, is now seen as a direct result of increasing atomic number and the repeating patterns in electron configurations. Let's zoom into the periodic table now and look at how the blocks S, P, D, and F divide up the elements. It's all based on where the last electron enters. In the S block, which includes groups 1 and 2, the outermost electrons go into s orbitals, like in hydrogen, lithium, or calcium. These are your typical reactive metals. The p block covers groups 13 to 18 with outer electrons in p orbitals. This is where you find nonmetals, metalloids, and even noble gases like neon and argon. In the center lies the d block, the transition metals, where electrons enter d orbitals. Think iron, copper, and zinc. These elements form colorful compounds, variable oxidation states, and act as catalysts in many industrial reactions. And finally, at the bottom, we have the F block, the lanthanoids and actinoids, elements filling the f orbitals. They're often radioactive and used in technologies from nuclear reactors to medical imaging. Each block helps chemists decode how atoms bond, react, and behave in different environments, from your test tube to the heart of a star. So let's wrap this up with a big picture view. The modern periodic law anchors the entire periodic table, stating that chemical and physical properties of elements follow a periodic pattern when arranged by increasing atomic number. This shift from atomic mass to atomic number brought clarity, accuracy, and predictive power. The structure of the long-form periodic table, with its periods and groups, not only organizes elements visually but reflects deep atomic truths about electronic configuration. By understanding S, P, D, and F blocks, we begin to see how different classes of elements, like reactive metals, stable noble gases, or versatile transition elements, behave as they do. The periodic table is not just a chart, it's chemistry's roadmap. It tells us which elements might explode in water, which will glow in lights, and which might form the backbone of future materials. I hope this session helped you connect the dots from atomic structure to periodic behavior. In our next class, we'll explore how trends like atomic size, ionization energy, and electronegativity shape the chemistry of these elements. Until then, keep exploring, because every element has a story, and chemistry helps us read it.